Welcome back. This is Keith Wiggins with PAG Waste Management, talking about the Handbook for Biomass Downdraft Gasifier Engine Systems. And we're on Chapter 6. This is Gasifier Fabrication and Manufacture. So, gasifier construction is a relatively simple task and can be accomplished in a well-developed shop using basic sheet metal and welding assembly techniques. Indeed, the task is so simple that it was possible for the countries of wartime Europe to construct almost 1 million gasifiers in just a few years, in spite of wartime shortages. Nevertheless, a number of new materials and fabrication techniques have become available since World War II, hopefully, and we shall call attention to these improvements in the discussion. The construction of a small gasifier, including the purification system, does not require sophisticated equipment or highly skilled mechanics. It can be built in workshops comparable to the auto repair shops found in most third world countries. Fabrication refers to the construction of a single gasifier for use or for an experiment. Manufacture commences when one undertakes the construction of a number of identical units. A general discussion of drilling, welding, and assembly procedures pertinent to gasifier fabrication and manufacture is beyond the scope of this manual. Instead, we shall comment upon specific techniques of fabrication as well as the wide range of materials specifically applicable to gasifiers. Materials of construction. Gasifiers are usually constructed from commercially available materials such as steel pipe, sheet, and plate. When choosing materials, one should, where possible, select those that are readily available and off-the-shelf equipment and materials that are available in bulk quantities. One should avoid exotic alloys, special shapes, and custom fabrication techniques that require large initial setup and tooling costs, except in rare cases where their use is justified. Smaller atmospheric pressure gasifiers require a minimum metal thickness of 20 gauge, with a double thickness reinforcements extending a few centimeters, like 1 inch, around all fittings and fastenings. The maximum mid-steel service temperature is 480 degrees centigrade. Although the metal temperatures encountered in a well-designed air gasifiers do not usually exceed the softening point of mild steel, certain stainless steels or inconel may give extra temperature resistance necessary for critical areas such as grate, hearth, or nozzles. Some of the mild steel components may suffer chemical corrosion in certain parts. Corrosion is likely to occur in areas where the water condenses or collects, since gasifier water often contains organic acids. Water collection is especially a problem in regions such as the upper magazine of bare gasifiers, as well as in some wet scrubber systems. In these instances, the steel should be replaced by corrosion-resistant materials such as copper, brass, epoxy, steel lined, or stainless steel as required. Stainless steel usually costs 2 or 3 times as much as mild steel and requires inert gas welding techniques. Copper and brass cost 5 times as much as mild steel, but can be joined by brazing or hard soldering, using the acetylene torch. Aluminum is particularly vulnerable to corrosion in alkaline environments and thus should be avoided there. Some wartime gasifiers, particularly the stationary ones, contain massive but fragile fiber brick insulation. We're fortunate today to have lightweight insulation materials based on spun aluminosilicate that are capable of withstanding temperatures of up to 1500 degrees centigrade, far beyond the requirements of gasifiers. The aluminosilicate insulation also offers many times the durability and heat flow resistance of fire brick at a fraction of the weight. It is relatively inexpensive and is available in a wide variety of forms. The 2 to 5 centimeter thick felt blankets and vacuum-performed cylinders, or silica sleeves, are particularly recommended for insulating the reaction zones. Moldable ceramics that come in wet putty can be shaped to the corners and edges and thus are also very useful. Finally, plastics can be used in certain applications. Some plastic pipe will perform acceptably up to the boiling point of water, is more flexible than metal pipe, and will not corrode. Plastic liners such as epoxy paints can sometimes provide the corrosion resistance needed in critical areas, provided temperatures are not greater than 120 degrees centigrade. So how to construct. A gasifier is built much like a water heater, and the same method of constructions are used. The workshop should be equipped with the tools for performing tasks such as shearing sheet metal, rolling cylinders, cones, drilling, riveting, grinding, painting, sawing, tube cutting, and pipe threading. An acetylene torch is valuable for cutting and welding tasks, but an arc welder is preferred for mild steel welding. When aluminum, stainless steel, or inconel is used, it will be necessary to use either a TIG, tungsten inert gas, or MIG, metal inert gas welding techniques. MIG is just a lot easier than TIG in the beginning for beginner welders. All seals must be made tight. Threaded and welded fittings are preferred at all points, and exhaust pipe type gaskets can be used if necessary. High temperature, anti-seize pipe dope should be used on all pipe joints. High temperature applications will require ceramic, fiber, or asbestos gaskets. Silicone sealant is appropriate at temperatures below 300 degrees centigrade, and rubber or Vuitton O-rings and gaskets will perform excellently at room temperature. The system should be leak tested before the initial startup as well as after modifications. Leak testing is accomplished by plugging the system and pressurizing it up to 25 centimeters per square inch of water with a blower. A thick soap solution is applied to all fittings and joints, and they are checked for emerging soap bubbles. Leak testing should also be performed as a standard test in regular maintenance schedule. Sizing and layout of the pipes. When designing a gasifier, it is important to keep the pressure drop in the system as small as possible because there are unavoidable pressure drops associated with the gasifier, the cyclone separator, and the cleanup system. It is very important to use the adequately sized pipe. The pressure drop associated with standard runs of pipes is shown in Figure 6.1. Engineering and plumbing handbooks also list the pressure drops associated with pipe fittings, such as the elbow and couplings. On the other hand, gas velocities within the pipe should be adequate so that the entrained solids will be conveyed to their proper point of removal, as shown in Table 6.1, rather than deposited inside the pipe. When laying out pipe connections for gasifier systems, it is very important to allow access to various parts that may require cleaning or adjustment. It is recommended that new systems be assembled with a large number of pipe unions to facilitate cleaning out the pipes as well as future design modifications. In general, it is better to use a pipe T with a plug rather than an elbow to allow for instrumental mounting and other additions at a later time. After a unit has been thoroughly tested and is in production, such provisions can be omitted. Instruments and controls. The gasifiers of the past were crude, inconvenient devices. Today's gasifiers are evolving towards safer, automated processes that make use of a wide range of present-day instruments and controls. An extended discussion of the system's instrumentation and control requirements is found in Chapter 10. Thermocouples, it's for temperatures. Thermocouples, such as chromal aluminum type K, should be used to measure various gasifier temperatures, especially below the grate, as a check for normal or abnormal operation. Temperatures at the grate should not exceed 800 degrees centigrade. Higher temperatures indicate abnormal function. Consequently, the signal from the thermocouple can also be used by a control system or an alarm system for pressure. Manometers are required to measure pressure drops across the bed, cyclone filters, and other components. Usually, these pressure drops amount to only a few centimeters of water pressure. The manometers are available as tubes filled with colored liquid, or more conveniently, bellow nanometers, such as the Dwyer Magnehelic gauge. Both types give a direct reading of the pressure drops that can be equipped with limit switches that will sound an alarm to warn when present flow levels have been violated, and/or active control valves to regulate those flows. And activate control valves to regulate those flows. Also, electrical transducers are available that convert pressure difference into electrical signals suitable for readout or control processing. Gas mixture. Oxygen sensors have been developed by the automotive industry to measure the small changes in oxygen concentration required to control the air-fuel ratio for clean, efficient combustion. They're relatively inexpensive and in particular can be adapted to gasifier designs for similar functions, though that hadn't been done as of that point. Automatic controls. The fact that an operator will be required for both large and small-scale gasifiers is a fixed cost scale factor that naturally causes larger systems to be favored. Automatic, unattended operation is therefore essential to the economic viability of small-scale gasifier systems. Automatic fuel feed and char ash removal equipment are already well developed for stoker-fed boilers and could be adapted to automatic gasifier operation. Finally, we can look forward to gasifier systems of the future that will use inexpensive microprocessors, that's funny, to integrate the signals from these sensors into the automatic and unattended operation of highly efficient gasifiers, making gasifiers as simple to use as a car or home furnace. You can't imagine what they would think of microprocessors back in the 80s, in the early 80s, of how far they've come. So that is pretty hilarious. Anyway, so that is chapter 6. Chapter 7, we'll get into gas testing. That's going to be a great one. We'll talk to you then. Bye.